I'm Jeff Yarger, professor of chemistry, biochemistry, and physics at Arizona State University. I've made a series of lecture notes on general thermodynamics that's really geared towards biochemistry or chemistry classes using thermodynamics, where I've gone through the fundamental concepts step by step without skipping any steps of all the fundamental concepts that would then be used to work specific problems in biochemistry, medical fields. Thermodynamics really has an overreaching view of a lot of macroscopic properties in any type of chemistry or biochemistry. So I want to just quickly introduce some of the topics in set number 4. I've made previous videos that cover the previous sets before this. And this one's really simple to introduce because it's really dedicated to looking at phase diagrams, starting with what we learn about in introductory chemistry, just single component systems and how things change, as I say, with function of, for example, pressure and volume or pressure and temperature, etc., different phase spaces, and how materials change as you change, for example, mechanical properties. But really the critical component here is as we get to chemistry, or as instead of changing for a single component system, like say, for example, water, where we're going to watch it, we're going to change its temperature and cause it to freeze into ice, or vice versa, take ice at low temperature and heat it up, or take ice and do something like increase its pressure and actually watch it melt, which is, kind of a surprising phenomenon and some of the unusual properties of water, etc. And that's looking at things like Clapeyron equations and basic phase rules. But really, the main component of this is getting towards the second half of these notes, which is covering when we change the composition of something. So looking at binary, trinary, in other words, multi-component systems, and how when you take a substance A and mix B into it, how does the phase diagram change as you change the composition of something? And some formality into regular solutions, how things can form eutectics. This is very critical in things like biological thermodynamics. For example, in the pharmaceutical industry, knowing how when you mix an active pharmaceutical ingredient with other things, and does it form, deep eutectics, and how do the different colligative properties change as you mix these different chemical components, is often really critical to understanding the system itself, is first understanding its thermodynamics. So I hope people in biological thermodynamics and chemical thermodynamics finds this, this set specifically useful in that regard. Thank you.